Assalamualaikum. Good morning. Can you hear me? Hello, can you hear me?
Yes, sir.
Yes, sir.
Thank you. So we move to example 1.2, third order system gain adjustment design. Okay, by looking at another examples, okay, where 0 is given at minus 1.5. Then the 3 open loop poles at 0, minus 1, and minus 10. Okay, so you are required to design a P controller. Okay, to yield a 1.52% overshoots. So 1.52% overshoots is referred to the theta value. Okay, damping ratio. And this will correspond to the theta. Theta is the angle of the straight line, damping ratio line from 0 intersection with the root locus. And from there, we will achieve a dominant pole. Also estimate the settling time, the peak time, and the steady state error. Okay, so that is typical for this kind of questions, TS, EP, and ESS. Okay, so closed loop, open loop transfer function is given, which is here, K multiplied by S plus 1.5 over S plus 1 and S plus 10. So if we multiply, is a third order system. Okay, third order system. The order is 3, and the type is 1, system type 1, because the given open loop transfer functions have a power of S power of 1, which is a open loop poles at the origin. Okay. Okay. So we derive the closed loop transfer function, which is CLTF. Okay. So we obtain this closed loop transfer functions. Okay. And from here, the characteristic equation is s cubic plus 11s square 10 plus k equal to 0. Okay, that is the characteristic equations. Why we have to know the characteristic equations? Because we want to know the value of the closed loop poles as k is varied on the root locus, especially when the root locus intersect with the imaginary axis. J omega. Okay. So the time response for closed loop at k equal to 1, okay, is given here. Okay. So not much that we can respond about it. Okay. It's just a third order system based on the closed loop. Okay. Time response always on the closed loop. It didn't fulfill our target, which is at zeta at overshoot 1.52%. Okay, there is no overshoot. Okay, no overshoot, but we want a 1.52% overshoot. Okay, so this response has no overshoots. So we have to start by looking the correspond zeta value that equal to 1.52% overshoots, the equivalent, which is 0.8. How do I get zeta 0.8? As I told you before, we have a three-way. One way, the first method is using the overshoot percentage formula, okay? And then straight away using a zeta value, okay? And then graph is given, okay, at 0.8, okay, yeah. So it's about over here, 1.52%, okay, at the bottom. If graph is not given, zeta value is not given, only one is given. So how are you going to find the zeta value? Okay, if number 2 and number 3 is not given. Okay, this is method number 3. Okay, this one is not given, this one is not given, and number 1 is given. So how do you derive that? Okay, how you get the zeta value? Okay, you just take the formula. Exponent okay, this one multiplied by 100%. So 1.52 multiplied by 100. So exponent by zeta, 1 minus zeta square. So you will get 0.0152. Okay. Then go to the next page. We apply ln. What is ln? Daniel, what is ln? Daniel. Sorry.
Loan.
Natural logarithm. Okay. So can you Daniel, can you find this one, please? Loan 0.0152. Daniel.
Hello, ada.
Calculator, please.
Negatif 4.186.
English, please.
Negative 4.186.
Thank you. So this one cancel out, simplify.
Progress.
So you can get zeta 0.8. Okay. Okay, guys. Clear, eh? So this one, if 1 is not given, 3 is not given, so you just insert here 1.52. 1.52. Okay. So if 1 is not given, 2 is not given, just 3. So this is the best method. In 5 seconds, you will get the value of zeta 0.8. So we draw the root locus as using the program, okay, by assuming k equal to 1, or you can follow my program previously, okay, and then you type the G, okay, and then you type R, locus G, and then grid, okay. So this is the root locus from the computer. So this is given, usually it's given in the test and exam, okay. So you don't have to worry how to plot it. So you just observe from this plot, okay. So what is our observations on this, Matthew? Matthew, what is your observations from this plot? Matthew, datang. Sami, hello?
Hello?
Sammy, are you there? Sami Labidi? So our observation is we have a 3 root locus path, which is the red one, the green one, and the blue. Okay. So this is the arrow. And we have over here, what point is this? Liana Camelia?
Yes, Doctor.
Point. With the arrow here. Break in or break out?
Break out.
Break out. Astaghfirullahalazim. Break in, Kak. Tak faham lagi tu. Okay, tak apa. It's okay, it's okay. Okay, learning, eh? Then it's going here in, 1 over here, 1 over here. And then there is a open loopholes minus 10. Liana again. What point is this? Liana Camelia again.
Yes, Doctor. Break in point.
Break in pula.
Break away.
Break away lah.
Break
Ayo.
out. Break away.
Break away, break out. Break out tu cerai. Break away. Break away point. Okay. Okay, so take note the break in and break away point ended at infinity. And infinity over here. Okay. So we have one break in point. We have 2 break point. The first one is break away, and the other one is break in. Okay, we have 3 root locus paths, and there is no root locus cross at the imaginary axis. Okay, right. So we want to know what is the dominant pole when zeta is equal to 0.8. So simply we print this. Okay, we print the root locus given, and then we use the protector. Okay, and put it at the origin, and then draw the straight line. But before you draw the straight line, you have to find the The theta. What is the theta value? Natra? Berapa? How many? Inverse cos 0.8.
36.86.87.
36.
Ah.
36.87
0.87.
degrees. Okay, which is over here. Okay, theta. So goes along. It will intersect the root locus 3 times. First intersection point, second intersection point, and 3 intersection point. So this case is special case. Previously, we have one dominant pole when the zeta line cross the root locus path. But in this case, we have a 3 times intersection between zeta and the root locus. So I zoom it. Okay, this one is not very clear, so I zoom it like this. Can you see? Okay, the damping ratio 0.8. It crossed 3 times, which is number 1, number 2, and number 3. Okay. So this is normal. Okay, this is normal. So come back to the intersection point. We have a 3 pairs closed loop poles, 3 pairs dominant poles as listed in the table. Okay, which is number 1, number 2, number 3. So it will create 3 cases. Okay, 3 cases or 3 pairs of dominant pole with 3 different gain values, which is 7.36, 12.79, and 39.64. Okay, and then the third poles also 3 values, minus 9.25, minus 8.61, and minus 1.8 with the different settling time, okay, and peak time, also the KV. Why the system is KV? Why? It's not KP. Why not KP? Why not KA? Why is KV? Patrick. Yo, Patrick, are you there? Patrick is absent. Simi Chin, why KV in this case? Why not KA or KP?
Average
Average. Average of what?
for the value go to infinity.
Ni
don't
orang
know.
salah.
I'm not sure.
It's okay. Simi Chin. So the system type is type 1 because we have a 1 over S. Remember? In the open loop transfer function, we have 1 over S. So system type 1, so system type 1 always correspond to KV.
Could you try again?
So what is KV? KV is the velocity error constants. Jot down.
I found
Velocity
this on the web.
error constant. Okay. Right, and then the steady state error will be 1 over KV. Okay, and as usual, this is the formula to calculate the gain K. Okay, TS 4 over real, TP pi over imaginary. So we look at the closed loop time response at K 7.36 at the first pair dominant pole. Okay, so you can see here there is no overshoot. Okay, but we want 1.53, 1.52% overshoot kan? So this one is not acceptable. Then we go for second pair, which is 12.79. So this one also no overshoots. Okay. And then the third one is I think the third one is okay. If you look here, this one is the peak is 1.03. 1.03, so the overshoot will be 1.03 minus 1 divided by 1 multiplied by 100%. Berapa? %, correct? And this one is 1.05 multiplied by 1 divided by 1 multiplied by 100, 5%. Then this one is, the overshoot is 1.1 minus 1 divided by 1 multiplied by 100. So it will be
10%.
10%. Okay. So 5%, 3%, 5%. So we choose the lowest one, 3%, which is near to 1.52%, because our target is overshoot 1.52%. Okay. So the root locus allow us to choose a proper gain to meet a transient response specifications. Okay. As the gain is varied, okay, we move through different regions of response. Okay. However, we are limited to those response that exist along the root locus only. Okay. When we play with P controller. That's why we need a flexibility. Okay. The issues here is it's not flexible. P controller is not flexible. P controller is not flexible. So we need a flexibility in the design so that can be increased by the response that are not on the root locus. Consider the desired response defined by overshoots and settling time. With gain adjustment, we can only obtain settling time at A to satisfy the desired overshoot. Point B cannot be satisfied, okay, with the gain adjustment, as shown here. Okay, point A yang tadi itu and point B. Because point B is not RL path. It's not on the root locus. Okay, as simple as that. So point B cannot be on the root locus with the gain adjustment. That's why we need a controller, okay, to design it so that it can go many points as long as it's not in the root locus. So how to do that? Compensators can also be used to improve steady state error. Okay, so this steady state error, the best one, target in design is 0, must be 0. Okay, it's not cannot be finite value. By increasing the gain, just now we increased the gain, we found that the steady state error reduced, but overshoot increase. Okay, if you see the graph, the 3 graph that I show you just now. Okay, compensators can be designed to meet the transient response and steady state error simultaneously. So this is the issue that we want to solve. Okay, so we have 2 configuration of compensation. One is cascade, the other one is feedback. So cascade meaning that the controller is connected serial, okay, serial with the plant. But for the feedback compensations, okay, the controller is connected, okay, as shown here. Okay, it's not parallel, but we call it as a feedback. Okay, a negative feedback. So the best one is here. We choose the serial one that multiplied with the plant controller. So PI controller is used to improve steady state error. Okay, so when we use P controller, sometimes we have a steady state error. So steady state error can be improved by placing an open loophole at the origin, okay, 1/S, as this increase the system type by 1. Okay, So I lay out again what is type 0, type 1, and type 2, as many students still confused. Okay, so type 0 always correspond to position error constant. And the formula of error is 1 over 1 plus Kp. So you have to find the Kp and then enter to the error formula 1 over 1 plus Kp. If your system is type 1, this one is S power of 0. This one is S power of 1. This one is S power of 2. If your system is type 1, like just now, so the error constant is Kv. The correspond error constant is Kv, okay? And the formula for error is 1 over Kv. But if your system is type 2, so the related error constant is Ka, okay? Is Ka, and the error is 1 over Ka. We call this one as a static error constant and system type. Okay, so this one is type 1. Please remember this one, guys. Okay, type 2 and type 3. Because we will use this Kp, Kv, and Ka in the frequency response as well. Okay? Everything okay, guys? Hello?
Still okay, Doctor.
Okay.
Okay, Doctor.
So how to improve steady state error? So that's why we have to look on the second topic of controller after P controller, known as proportional integral controller, or PI. Okay, pi controller. Okay, P and I together, it become PI controller. Okay, so consider a system operating at a desirable response with a closed loop pole at A. Here, A. By adding a pole to increase the system type, A is no longer a closed loop pole. Okay, it's no longer a closed loop pole. Okay, so therefore, you can see that. Okay, this one is P controller, and this one is the PI controller. Okay, because we adding 1 over S to the system. To solve zero close, to solve this, zero close to the pole and the origin has to be added. Okay, thus A is now a closed loop pole. So we improve the steady state error without affecting the transient response. That is important. Okay, so it's like a dummy. Okay, you insert the S plus 0.01 over S. So it's like a dummy. If you plot on the S plane, okay. So this is the zero, sorry, the poles, and the zeros is very near, okay, to the origin. Okay, so, okay, it cancel each other. Okay, it cancel each other, poles and zeros, but system type increase. That is the important one. Okay, that is the important one. So if you look here, S plus 0.01, okay, the zeros is minus 0.01. And this one is, the poles is 0. So you can see that this one is very near. Okay, if you plot on the graph on the S plane, is very near. So the effect is not much on the transient response. So therefore, we use this kind of configurations, PI controller connected serial with the plant. Okay, then you can see that the root locus, okay, is going through point A again. Examples. John Chuan. John Chuan. John.
Dr. Ijimi.
Yeah. Can you read the
Oh.
question, please?
Okay, example 2, given a system operating with a damping ratio of 0.174, show that the addition of the PI compensator reduces the ESS to 0 for unit step input without affecting transient response.
Sure. Okay. Without affecting transient response. So this is a block diagram before compensation, before controller design. And then this one is after compensation design. So engineering is like that. Okay. You always make comparison before and after. Okay. Right. Real and estimation. You make comparison. Okay. Right. So now we introduce a compensator S plus 0.1 or over S. So you can choose any number as long as the zeros is very near to the origin. So maybe C Michin don't like this S plus 0.1 over S, and she choose S plus 0.01 over S. Can or not? Yes, can. Okay. And then Nur Atika, she don't like 0.01, so she choose 0.001 over S. Can or not? Yes, can. Also right. But if you choose S plus 100 over S, this one is wrong. Okay, so cannot be far away from the origin. So you can choose 0.1, 0.01, or 0.001, as long as the number is very small and the location of 0 will cancel out the poles at the origin. So we draw the root locus. Okay, so we draw the root locus, and then we take the protector, put the origin, and then we measure the theta. Okay, Safwana, what is the angle of the zeta line? Hello, Safwana.
Yes, Doctor.
Angle. Senang je.
$100.02.
Astaghfirullah.
I don't
Jauh,
know.
eh?
It's
Inverse cos 0.174.
sorry.
Batuk, tak sihat.
Sorry, Doctor. 79.97, 0.98.
7.
79.98.
Thank you. Okay, so theta is here. All right. So the dominant pole is minus 0.694 plus J 3.926. Okay. So we calculate the error first. Okay. So system is type what? Type apa ni? Ridwan. System type. Ridwan.
Saya Ridwan ke, Doktor?
System type.
Type 1 kot, Doktor.
Type 1. Tak faham lagi tu. Syah. Fikri. System type.
Ya tu. Saya rasa saya sama jawapan dengan Ridwan.
Berapa? 1. Type 1. Type 1.
Ya betul.
Yang kau tu gambar tu macam 2 nampak. Type 2.
Doktor, type 0.
Type 0. Okay. Fikri, you punya profile macam gini. Type 2. Salah. Type 2 salah. Type 1 salah. The correct is type 0. Okay. So still don't understand. Okay, type 0. So if type 0, we use KP. So KP is limit s to 0 kgs. Okay, and the error is 1 over 1 plus kp, and the dominant pole is s square plus 1.388s plus 15.892 equal to 0, which is this one. Okay. So for a damping ratio 0.174, okay, the dominant poles are here, okay, and the gain is 164.6. Okay, so gain can be calculated using length and using the substitution of minus 0.694 plus J 3.962 ke dalam open loop transfer function magnitude. Okay, two-way to calculate. So the third pole is minus 11.61. And okay, so minus 11.61. So the second order approximation is minus 11.61 divided by 0.694. 16.73 greater than 5. So second order approximation is valid. Okay. And therefore the KP is 8.23 and steady state error is 0.108. How to calculate the third pole? Okay, so we take 165, okay, integer number, okay, 164.6 from 164.6. So we make it 165. Use trial and error from the gain at the dominant pole, which is here. Then this is the characteristic equations. So you insert the S value here, sorry, the K value, which is 165. Then you find the roots. Okay, so the roots is minus 11.6 minus 0.69 plus minus J 3.93. Okay, so that's why we get 11.36 here. Okay, 11.61, sorry, 11.61 is the third pole. So again, you can see that the third pole is here. Okay, this one, dominant pole at K equal to 165. Okay. So we simulate the time response, the closed loop time response. Okay. At here 165. Okay, closed loop transfer functions. So you can see that the final value is 0.892. So the steady state error is 1 minus 0.892, 0.108. Okay. So steady state error exists. So this is not good. Okay. That's why we adding PI controller at the poles 0.1. So S plus 0.1 over S, the PI controller, okay, with the same damping ratio, with the same dominant poles, okay. So we get the K value now is about 158. Okay, so not far away from 165. Okay, not far away from 165. After we insert this S plus 0.1 over S, and then we draw again the root locus, so it's not far away. Okay, so compensated closed loop poles and gain are approximately the same. That important. It's not far away. Okay, beza sikit apa? A little bit difference, no problem. Okay, but give the same transient response. That is matter. That matter. Okay. However, with PI controller system is type 1. Okay, become a type 1, and steady state error become 0. Previously type 0. So when we apply PI controller, it become type 1. Because PI controller will increase the system type and make the steady state error become 0. Then we plot again. Okay, plot again, then we get the same root locus as previous, even though we combine S plus 0.1 and S, because this one looks like a dummy. Okay, we don't disturb anything. Okay, this is the poles and zero cancellations that increase the system type. That's all, and make the steady state error become 0. And after we run the time response, okay, with S plus 1, S plus 0.1 and over S multiplied with the open loop transfer functions, okay, so we multiply together, then we run the closed loop response, then we get the steady state error here. The final value is 1. Okay, the input is 1 volt unit step minus final value over 1 divided by 1, the final value. Okay, so you get 0. Okay, so steady state error is 0. This is our target, to make the system steady state error 0, maintain transient response, okay, maintain the overshoot. So when we compare, you can see that before and after. Before PI controller, after PI controller. Nick Muhammad, can you comment this graph? Nick Muhammad,
Comment.
can you comment?
Faster transit response. No steady state. 0 steady state.
No steady state error and 0 steady state error is two different things.
Sorry, 0 steady state error.
ESS 0. Okay.
Good.
ESS 0. Right. Okay.
That's all right.
That's all. Yeah. That's all. Transient maintain. Okay. Overshoot pun maintain. 1.5. Nampak? 1.5.
Yes.
Any question? Uncompensated ni before lah, before design. The book said uncompensated, okay? And then ideal integral compensated is after. You can see two graph here, the blue one and the black one, okay? So the input is step. So in general, you can say that the transfer functions of PI controller is this one, GPI KP plus KI over S. Okay. So we multiply, so we get K S plus Z over S. Okay. KI over KP. Okay. The Z, okay, the zero value is KI over KP. So implementations, log diagram is K square over S, okay, parallel with the proportionals, then connected serial with the plant, okay. So this one is a PI control. So PI controller is designed by adding a pole at the origin and 0 at S minus Z. 0 is chosen to satisfy the transient response specifications and can be adjusted by varying KI over KP, the ratio. If the same transient response as the uncompensated system is required, choose the 0 close to the origin. 0 close to the origin. For example, minus 0.01, minus 0.01, and so on. Do not choose minus 100. Okay, it's totally wrong. Here, okay. So another examples for PI controller is this one, example 2.1. Okay, so you are given open loop transfer functions. Okay, So we have a issue here, design a PI controller to achieve transient response as the following. So this one, we call it as a spec design. Okay. Spec designs. So 10% overshoots, zeta 0.59, okay, using graph or formula. And target is 3.2 second settling time, 0 steady state error, and verified design using MATLAB. Okay, so we use the MATLAB. Everybody, can you see the MATLAB, guys?
Yes, Doctor.
Okay. G is equal to, assume K equal to 1 over S square plus 2.5S plus 1. Okay. And R locus G. Okay. Right. So I share the plotting. Okay. Ahmad Faleh. Ahmad Faleh. Can you comment on the plot?
They have a 4 okay.
2 root locus path.
Plus and
No root locus intersect the imaginary axis. And how many breakaway and break-in point?
breakaway 1.
1 breakaway. Break-in?
Break-in also 1.
Not exist. Bukan kosong.
Ada.
Not exist. Aduh, udah. Astaghfirullahaladzim. What is the value of breakaway point?
Breakaway point 1.
Tengok tu. The drawing. Breakaway point. Tak tahu. Zulhelmi, what is the value of the breakaway point? Tak datang.
0.562.
0.562. Astaghfirullahaladzim. Denson, what is the value of the breakaway point? The breakaway point actually is the pole, the closed loop poles. Can't hear you.
Negative 1.25.
Yes, sorry. Negative 1.25. And then we want to find the zeta 0.59. So how can we do that? Wenjin. Wenjin, datang. How you want to draw zeta 0.59 on the root locus path?
Hold on. I scroll back.
Scroll back. Yeah, I already scroll
My
back.
notes.
Oh, you scroll back your notes.
Oh, there you go. The 0.5.
No need lah. Yeah. That's great. Zach. What? Wenjin. That's great. That's great. Look at the Zoom. As
Not
grid.
see the delta.
Nampak?
I only can see the Z equal to, yeah, S grid Z
Ah,
and G.
as grid, bracket, Z,
Z.
Jack,
Yeah, sorry.
comma,
Comma G.
Jack, Jack, comma,
G, right?
zero. Zero, eh? Right, so we share again the plot. Okay. So can you see the intersection point? Can't see. So you have to adjust the scale. Okay, adjust the scale, the imaginary axis. Okay, choose maybe 3 and 3. Okay, can you see? Yeah. 5, 9, okay. Ivan, Miss Ivan, what is the dominant pole?
Yes, doctor.
What is the dominant pole?
Negative 1.25 plus J 1.7.
1.7, okay, session A. Okay, so we come back to the slides. Okay. Okay, come back to the slides. Therefore, we plot it. Then we may calculate the error. The gain over here is 3.5. So we insert here. Don't forget to insert the K value. So the student let this one as 1. So actually it's wrong. So you have to insert the 3.5 inside the formula. Then the KP is 3.5. So 1 over 4.5 is 0.22. So this is not good for error. Okay. So we have to improve it. Okay, so this is time response based on the closed loop transfer function 3.5. Okay, so we can see that 0.778. So 1 minus 0.778 is 0.22. Okay, so as Ivan told us just now, the dominant pole is here. Okay, so we introduce the PI controller S plus 0.01, okay, over S, okay. Then this is the open loop transfer functions. Then we resketch the root locus again with PI controller, okay, to make sure that we have the same transient response and 0 steady state error. So we draw again, okay, 0.59, more or less about 3.48. This one doesn't change much, okay. Okay. And when we calculate the error, so the error now KP, okay, so this is your KP, 3.5 S plus 0.01 over S, this is PI controller. 2S plus 1, 0.5 S plus 1 is the open loop transfer function, is infinity. 1 over infinity is equal
Sorry,
to
doctor.
0. Sorry.
Doctor, I think you didn't share the whole things, but share the
Right.
different document. You are sharing the slide. Yeah.
All right. Okay. Sorry.
Doctor.
PA. This one. Oh, sorry. I should share this one. Okay. Okay, this one.
Yeah.
I repeat again. Okay, I repeat again. So sketch the root locus. Okay. We plot it, and we have a steady state error 0.22. Then we plot the time response before PI controller confirm 0.22 error. Okay, so Ivan said this is the dominant pole. Okay, Then we introduce the PI, okay, and multiplied with the open loop transfer functions. And we want to see the overall system. The replot of the roller curves give the same transient response and zero steady state error. We plot again, okay, so we get 3.48 confirm, minus 1.25 plus minus J1.7 confirm, and the error is equal to 0, which is 1 over infinity. Comparison before and after PI, okay, so this one is before. You can see that the final value here 0.778, and this one final value is 1, okay, so it takes a longer time to reach the error equal to 0, but after about 600 seconds, the system become steady state error equal to 0. Okay, so it takes time to reach steady state error at time is equal to 600 seconds. Okay, so steady state error reduced from 0.22 to 0, which is good. Okay, and settling time longer after PI controller, and this an issue as well. Okay, so how to shorten the settling time? So this the solution is after the break. Okay, after the break. Any questions? Any questions?
Yes, doctor. Can you
Yeah.
see the chart?
The chart, the graph, the graph.
No. Sami actually is asking.
Yeah. You want to see the
the chart?
The chart.
Yes.
This one.
In the Zoom meeting.
This one.
No. I mean.
The chat. Oh, the
Yes.
chat. Oh, stop for what? Doctor, I'm having trouble setting up my mic. Couldn't connect in, but I am present. Okay. Doctor, it's better to have a smaller number than 0.1, or is it the same effect? A smaller number than 0.1. Yes, 0.01. Okay. 0.001. Okay. As long as it's very close to the 0 value. Did I answer your question? No better. Okay, 0.1 or 0.01 or 0.01 doesn't affect the transient response. Okay, the three numbers as I told you just now definitely will give the steady state error 0. Even though it is big or even though it's small, okay, but must be 0.1, 0.01 or 0.001 over S. Did I answer your question? Shukran. Okay, guys, 10 minutes break. Okay. 10 minutes break. Okay.
Okay, doctor.
Okay, guys, we continue. Can you hear me?
Yes, doctor.
Okay, so I already WhatsApp you the chapter 2B. Everybody receive? Hello?
Yes, doctor.
Okay, all right. So we continue. Chapter 2B. Sorry, there is B here. Can you insert B inside? Okay. Chapter 2B, PID control design. So we already go through 2.1 introductions, 2.2 design with gain adjustment or P controller. Design PI controller to remove steady state error. Okay. And then now we are moving to improving the transient response. As the last first half lecture just now, it takes a longer time, about 600 seconds, to achieve steady state error 0. So this is a problem as well because it's slow. Okay, so we don't want 600 seconds. Okay, 600 seconds is about 10 minutes probably. Okay, 10 minutes in order to achieve steady state error 0. So we have to improve and faster. Okay, fasten the transient response. Okay, by using a PD controller. That's why to improve the transient response, we introduce proportional derivative controller. Okay, PD controller. PD controller is used to improve transient response and maintaining the steady state error. Okay, maintain the steady state error. This is carried out by adding a single zero to the forward path. Okay, single zero to a forward path. There is no over S. Okay, on the feedback control system. This can be represented by this block diagram. K1 and K2S connected parallel, and then we simplify, so it become K KD multiplied by S plus KP KD, where Z is equal to KP divided by KD. Okay. Okay, guys. Okay. Then connected parallel, serial to the GS. So you must choose a proper selections of 0 value in order to improve the system transient response. For example, okay, you have an uncompensated system here. Okay, with is a 1, 2, 3 as a third order system. Okay, open loop pulse at -1, -2, and -5. So the root locus is shown in the blue color, and let's say it is operated at zeta 0.4. Okay. So what is the value of theta for zeta 0.4? Yuvarajan, are you there?
Yes, doctor.
Inverse cos 0.4, please.
0.4, 66.42.
66.42 degrees, okay, which is over here, theta, okay.
Yes, sir.
And the dominant pole is 0.939 plus J 2.151, okay, at the gain value 23.72. Then we introduce 0, which is S plus 2, which is connected serial with the plant. So zeros -2 is over here, okay, beside -1, and overlap the open loop poles -2. Okay, so you can see that the root locus now change from curvy to straight line because Open loop poles -2 cancel out by the open loop zeros -2. Okay. So it's cancelled out, right? And then we insert 0 -4 at 0 -4 and see what happened. The root locus also change. Okay. Gain value change, dominant pole change, and then 0 -3 also. The curve change, the root locus change, the dominant pole change, and the gain value also change. Okay, so let's see the time response. If we choose, this is uncompensated before PD controller, is the closed loop transfer functions. Okay, so we obtain that the settling times is 3.75. Okay, settling time at 3.75. That's too long. Okay, that's too long. And TP 1.64. Then we use we add 0 at -2, so it becomes S+2 in the transfer functions. And we observe the settling time. Now the settling time has been shortened from 3.75 to 1.12. Peak time as well. Okay. Then we change, instead of S+2, we change to S+3. Okay, S+3, so it increased a little bit, but still not 3. 1.38 seconds. And then we observe S+4. We introduce 0 at -4, and the settling time is 1.8 seconds. And peak time is 0.715 seconds. Okay. So when we compare, okay, the uncompensated, which is A, you can see that the peak time is 1.64 seconds and 3.75 seconds for settling time. So this is EP, this is TS. But when we add zeros at -2, okay, so the peak time now has been shortened from 1.64 to 0.461, meaning more faster, and 1.12 settling time, which is settling time is faster. Okay, the final value settle faster at 1.12 seconds. And at zeros -3, a little bit increase, but still better than the uncompensated. And at S+4 is 0.715 and 1.8 settling time, and still better from the uncompensated system. So it seems that this one is by looking at the closed loop transfer function time response, the peak time and the settling time is faster. Okay, the peak time faster, the settling time faster. So it's a good choice of 0 -2. So the system is all compensated at 0.5 damping ratio. Okay, for the compensated system, the closed loop poles have more negative real and larger imaginary part as compared to the uncompensated system. Thus, the compensated system operates with a shorter settling time and shorter peak time. So system B gives the best transient response. So in summary, to adding a 0 on the forward path improve the transient response. So we must have a proper selections of the 0. So if we do like this, okay, insert one by one, -2, -3, and -4 take a longer time. So a lot of work have to be done to observe the time response, to observe the root locus, to observe the dominant pole, and so on. So it's not practical at all if you do like this. Okay, so this is the comparison, 4 graph in one graph, four response in one graph, okay, which is the uncompensated -4, -3, and -2. This one is the best one. Okay, so that's why we have to do another technique rather than do 4 time response closed loop, do 4 root locus. So we have to use the calculations in order to find the PD controller. Okay, so this examples is given here. So we can see that this is the open loop transfer functions. Design a PD controller to yield a 16% overshoot. So this one you will get the zeta value, okay, with a 3-fold reduction in the settling time. What do you mean by 3-fold reductions? Okay, so if the pole 1 is equal to 3 seconds, so the new settling time will be 1/3 multiplied by 3, 1 second. Okay, that is the meaning of 3-fold reductions. Check design using MATLAB. Okay, so now we know that this system K S plus 4 S plus 6, okay, is a type 1. Why type 1? System type 1 because it's S power of 1. 1 poles at the origin. Okay, so system type 1. So we identified we have a 3 open loop poles. Okay, meaning that we have a 3 root locus path and no zeros. Type 1, as I told you before, determine zeta and theta. So zeta is 16%. So what is the corresponding value of zeta? Nur Aina Wahida?
Yes, doctor.
What is the zeta value? The equivalent
79.
Zeta value, the equivalent 16%. Overshoot.
80.79.
80.79. Apa ni? Degree. So zeta dia berapa?
0.704.
0.504. Stop. Wah, puasa kan? Apa? Maaf. Okay, the zeta value is 0.504, and then the theta is 0.50. Berapa? Wahida? Cos inverse 0.504. Wahida?
59.74.
Huh?
59.74.
Tapi yang ini apa? Ni.
Oh, itu salah kira.
Salah. Salah. Pakai tangan je. Saya padam Astagfirullah. So determine then we get the value here by determine the intersections point between RL and zeta line to get the dominant pole. Okay. Find the gain value at this point. This is the steps. Okay. Find the third pole at this gain value. Check the validity, check the validity. Is it valid or not for second order approximations? And calculate the steady state error. ESS that identify their desired specifications. Right. Okay. So we plot. Okay. Like just now, we plot. Jason.
Yes, sir.
Jason, what is your observations of the plotting?
Yeah, just a second. 3 locus root.
3, okay.
And
Okay.
there will be a break. Yeah, that point.
Breakaway.
Yeah,
Breakaway or break in?
There will be a breakaway.
Okay. And 3 RL ended at infinity. 1 E sun. Okay. Okay. Okay, what else? What else? Ismail. What else?
Yes, doctor.
What else, Ismail? From the graph.
The intersection point
Ah,
with the imaginary axis.
has a dominant pole.
Oh, yes.
And has a?
Dominant pole.
Ah, has a pole.
Yes. Negative 1.2 and 2.07.
Then the damping is 0.503. Okay, this is the angle, right? So you know how to do it, okay? And then what is the value of the third pole? Ismail,
Yes, doctor.
third pole.
Negative 7.6.
Shukran.
Afwan.
7.6. Okay, so we plot the closed loop time response. Okay, so you can see that the gain is 45.3. Where this gain come from? This come from here. Okay, 43.5 here. 43.5. Stop. 43. Okay, so the settling time is 3.47 side, and peak time is 1.68 seconds. Okay, this one is before PD control. So to improve the transient response using a PD controller, okay, so we have to, based on the spec design, okay, which is this one, spec design. Our target, okay, zeta 0.504 or 60% overshoots, okay. And we found that the dominant pole is here, as Ismail said just now. Okay, so we find a new time response, which is TS 4 divided by real. Okay, so where did the real come from? The real come from here. Okay, 1.205. Divide 3.32 second, and then TP pi divided by imaginary. Where this imaginary come from? This imaginary come from here, 2.064. So pi divided by 2.064, 1.52 seconds. Okay, the system is type 1. So due to type 1, so you have to use KB. Okay, we cannot use KA, we cannot use KP. So we use KB. So limit SGS, S to 0. So 43.5 divided by 24. So the KB value is 1.8. Okay, this one is 1.8. Insert inside, so we have an error 0.5. Okay, 0.55. So to get 60% overshoot, the closed loop pulse can be found at here. Okay, at this point. Okay, so with TS 3.32 seconds and TP is 1.52 seconds and K error is 0.55. Okay, so the third pulse is occurred at minus 7.59. Okay, this one we get this value from the characteristic equations. Okay, and we insert the value 43.35, and you get the S cubic. Then you can know what is the third pole. The desired spec is we want this settling times threefold reductions. So the old value, the settling old value, the TS 3.32 need to be divided by 3 because we want a threefold reductions. So that's why we get 1.107. Why 3? Because 3 fold reduction. Understand, guys? Understand, eh? Okay, so now the TS become 1.107, which is the target. And the desired closed loop pulse here, as mentioned here, is minus 3.61 plus minus J 6.193. So therefore, we have to calculate the new real and the new imaginary, because it's already 3-4 reductions. So we have to include 1.107. Okay, so this will become a new one, new real. Okay, so the new real will become 4 divided by 1.107. Okay, then the omega n. Okay, so the omega n will become 7.17. Okay, now the real closed loop pulse is minus 3.613, and the new imaginary is J 6.193. And the new closed loop pulse, okay, to fulfill the spec design is the spec design, which is 16%, and new 1.107. Okay, 1.107. So this is the new one. We are not using the previous dominant pulse. We are using the new one, okay, with updated spec design. So this dominant pole, the new one, will be put here. Okay, so will be put here, okay, as the new operating point. Then we have to calculate the value of the angle. Okay, so let's say this one minus 6 theta 2, minus 4 theta 3, minus z, okay, theta 4, and then 0 is theta 1. Okay, so we just put the new zeros over here. Okay, you can put over here as well, no problem. You can put over here, no problem. It's just assumptions. Okay, we locate at here between 0 and minus 4. Okay, some student will ask, why you put here? Why you put here? Why you put here? Actually, you can put anywhere as long as it's on the real axis. So we calculate the corresponding theta. Okay, theta 1 is 59.7, which is over here. Okay, theta 1, sorry, theta. This is theta. Okay, theta 1 is 180, 120 minus 26, which is over here. Theta 2, 86.42, which is over here. And theta 3 is 68.92, which is over here. So theta 1 plus theta 2 plus theta 3 total due to poles, okay, minus theta 4, because theta 4 due to 0. Okay, so this is what I call the angle criteria, equal 180 degrees. Okay, so theta 1 is 120, theta 2 is 86.42, theta 3 is 68.92 degrees, minus theta 4 is unknown because you want to know the locations, equal 180 degrees. So therefore, theta 4 is 95.6 degrees. Okay, so this, the 0 is calculated using angle property, which is shown here. Okay, so the angle is 95.6, which I shown previously. So thus, if you look at here, 95.6 is will give you the value. Okay, the value is minus 3, which is here, minus 3. Okay, so minus 3 is here, minus 3. Okay, and the real part of dominant pole is minus 3.613, and automatically the x here is what? The x there is 3.613 minus 3, which is 0.613, the length. Okay, the length of x. Okay, and this part okay, the length of this part, sorry, this part, okay, is 6.193. So x is equal to 6.193 divided by tangent 84.4 degrees, okay? Tangent 84.4 degrees, x is equal to 0.607. That's why z is equal to minus 3.613 plus 0.607. So that's why you get minus 3 value. Okay. So we replot, okay, replot the PD controller root locus with PD controller root locus, open loop, okay. You can see that the locus now has been changed, okay. Has been changed as shown here, okay, because this one is start from zeros, ended at here, and this one is 2 poles, breakaway point, one goes up, one goes down, infinity and infinity, okay. And the time response, okay, with PD controller, it is a closed loop, okay, transfer functions, 1.15, okay, and this one is settling peak time, 0.522, and settling times 1.15, okay, 1.15. So if you look here, we already achieve the spec design at TS 1.15, i.e. 3 pole reductions. So the complete root locus is shown here. Okay, you can see that this one is before design, this one is after design. Okay, so the settling time much faster, the peak time much faster. Peak time over here, PP, settling time, new. This one is a peak time, full settling time. Okay. So we achieved that the new location of 0 is -3. So this one is S plus 3. And Kp over Kd is equal to 3. Okay, and automatically Kd is 47.45 and Kp 142.35 by using this ratio. Okay, so the complete system is 47.45 multiplied by S plus 3 over S plus 4, S plus 6 multiplied by S. And when we see the time response, okay, before and after PD controller, so you can see that we have improved the system, okay, improve the system, the transient, okay, from 3.47 to 1.15 settling time and 1.68 peak time before compensator, it become 0.522 seconds. Any question? Any question, guys?
No, doctor.
Faham? Irfan? Do you understand?
Yeah.
Yes, doctor.
Yes, doctor.
Any question? Okay, if no question, we move to the second examples. Again, PD controller. This is a test question. Previous test question. I don't know what year is it. So for a unity feedback system with the open loop transfer functions, this is open loop, 50 over SS plus 5. So observe it. Open loop poles, -5, 0. System type 0. Okay. Open loop zeros not exist. Gain 50. Okay. So determine the overshoot percentage and settling time of the system. Okay. Design a controller to have a 50% reductions in the OS. 50%. So if the OS, the old one, let's say 5, okay, 5%. So the new overshoot will be how much? 5 divided by 2, 10. So 2.5%. Okay, reduce the overshoot. And 4-fold improvement of the settling time. Just now 3-fold, but now 4-fold. So let's say the old one, let's say it's 4 seconds. So the new one will be 1/4 multiplied by 4, 1 second. Okay, that is the meaning of 4-fold improvement. 3-fold reduction. Okay, so you must understand the word. So find the closed loop transfer function, 50 over s plus 50 plus 50. Okay, this is the closed loop transfer functions. Okay, so do we need to draw the rule locus on the system without controller? Can we find the specification needed? Yes, this is given. So you can compare this one with the standard second order transfer functions. So omega n is square root 50. Okay. Okay, how much? Omega n square root 50. Zarif,
Yes, that. Yes, that.
square root 50.
11.07.
11.
11.07.
Radian. Square root 50. Square root 50. 7.
7.07.
7. Okay. So the OS is 30.45% and the TS is 1.6%. Where this come from? This one come from this one. Okay, from the plotting. Okay, so you can see that it's over here 0, 50. So this one is what? Liana Camelia. Kak, Liana Camelia.
Yes, sir.
Point tu. Break apa? Break away point. Lambat point, and then the zeta here is 0.356. Okay. And the dominant pole is minus 2.5 plus J 6.56. Okay. And the overshoot is 30.2. There. Overshoot 30.2. And the settling time is, you have to calculate. Okay. So 7.07 and the zeta is 0.356. Okay, by calculations. OS is by using a formula C. Okay, so you have to use the formula inside the value zeta 30.5 and settling time is 1.6 seconds. 4 divided by zeta omega n. Okay, it's by calculations where the rule locus is given. But our desire is we want to reduce 30.5 into half, 50% reductions. So 30.5 divided by 2, 15.25. Okay. And then zeta still maintain and settling times is 0.4 seconds, which is 1.6 seconds divided by 4, 0.4 seconds. So that is the target. Okay. So that's why we have to calculate the new omega n by using this formula. TS equal to 4 divided by zeta omega n equal to 0.4 seconds. So the new omega n is 19.4 radian per second. Then calculate the new dominant pole, okay, the real part, which is -10. Then calculate the new imaginary part of the dominant pole, which is a 16.73. And now the new dominant pole is -10 plus J 16.73 will be the operating point, the new operating point here. Okay, the new operating point. So now we have the open loop poles, which is 0. And then we have the open loop zeros, which is -5. -5 ke -50? -5. Okay, -5. Okay, this is open loop poles. -5 and open loop zeros minus open loop zeros. Okay. So when we want to locate the zeros, the new zeros, so we locate here. Let's say we locate here. Okay. And then we calculate the theta 3, we calculate the theta 2, and we calculate the theta 1. Okay. And then the length 1, the length 2, and the length 3. Okay. But if you don't want to use L1, L2, L3, you just use magnitude. Okay. S plus 5, then you insert S minus 10 plus J 16.73 inside. Okay. You also will get the value, which is 15, same. Okay. Instead of Pythagoras, you can calculate the shorter way using this formula. So calculate the theta 1, theta 2, and theta 3. Okay, so theta 3 will give you this angle. Okay, theta 1 plus theta 2 minus theta 3 equal to 180 degrees. Okay, so theta 3 is this angle. Okay, so the PD controller now is Kp over Kd, which is 25.29. Okay, then multiply by 50 the existing gain, so it will become 15 and Kd 0.3. Okay, so now the complete system is 15 S plus 25.29 S over S squared plus 5S plus 50. Okay. Right. We stop here. Okay, so when you apply a PD controller, okay, when you apply a PD controller, you can see that the settling time has been reduced 4 times, and the overshoot has been reduced 50%. Okay, as shown here. Any question, guys? Any question?
No.
Oh, ngantuk. Ngantuk, lapar. Hah? Ada soalan? Chung Hui, any question? Tak datang. Kau, Hao Leong, any question?
Doctor,
Yeah.
can I ask for the final after we put the PD? Is it necessary for the value to be exact? If it's more than 50% reduction, so it must be 50%, or it can be plus minus, because I can see from the notes.
Dia lari sikit. Okay, doesn't matter if the value a little bit change, not the same. Okay, 0.1, 0.2, 0.3 is okay, as long as in the range of acceptable. Okay. Chua, any question?
No, doctor.
Understand? Kwan, any question? Okay, guys, I think that's all. So we see you again on Wednesday. Okay. So see you on Wednesday. Okay. Thank you very much. Bye.
Thank you.
Thank you,
Doctor.
Doctor.
Thank you, Doctor.
Doctor.
Bye.
Doctor.